Well, folks, welcome to the XSEDE Big Data Workshop. We have a full day ahead of us with lots of interesting content. I probably don't have to convince a lot of you of that since we have a full audience today. This is our largest workshop yet. As we expand our attendance cap here, we're really pushing it. So today we have nearly 400 of you out there. So one thing is the sites, please maintain pretty good discipline on your mute. If you don't keep yourselves muted when you're not asking questions, which you are very much encouraged to do, we will have chaos. So please be aware of that. Otherwise, welcome to all of you. Again, we have a large roster of sites out there. I think it reflects the interest in the topic because this is an exciting and interesting area of computer science, high-performance computing to be involved in. So welcome to all of you sites. You're going to see a bit of me today. I'm John Urbanek. I'm a parallel computing scientist here at the Pittsburgh Supercomputing Center, which is the host site that we are broadcasting from. I spend most of my time parallelizing codes. And these days, that amounts to an awful lot of big data and machine learning work, and we'll see how all this stuff relates as we go through the day. You will also be hearing a good bit from Brian Gill later, not too much later actually, who has an extensive amount of expertise in not only using this stuff but administering it. So you have the ability to talk to a guy who's got a lot of very much not just hands-on experience, but elbows deep in the guts of this stuff experience. We are pretty much good ways through our yearly monthly workshop schedule here. We are on August already. We've had what I think has been an successful and fun year so far with a lot of topics. Next month is our MPI workshop, which is our only two-day workshop in our rotation here. Which brings me to the point of our agenda today. These workshops are only as long as they should be. We value very much your time. So we don't have a lot of padding in any of our agendas here just to fill the days out because people have flown in from somewhere to attend these. But we do try to cram in everything that we possibly can. This particular agenda for this workshop is really crammed because we're right on the cusp of there's all kinds of extra stuff that I'm tempted to make this 2 days, but we're trying really hard to keep it 1 day because 2 days is a much bigger commitment for a lot of you. So it'll be a packed day. We're dealing with different time zones here. And we realize your lives don't come to a halt. But we also don't want this to be some kind of offline webinar experience. The idea is this really is very much a classroom experience. It's not a MOOC. I'm not just a talking head and you're out there in space and don't have recourse to ask lots of questions. Very much we encourage questions and there's lots of hands-on today. We encourage you to really try things out and you should leave this workshop feeling like you've actually exercised what you've learned here. You haven't just heard a lot of buzzwords. So our agenda, as I said, is pretty packed here. I'm going to give you kind of an overview of a lot of big data concepts because there are a lot of concepts. There are a lot of interesting and moving parts in this field. It's one of the things that makes it so exciting. Then Brian will give you very much a grounding in what is the classic kind of technology to enable big data, which is Hadoop. Many of you would feel absolutely gypped if you didn't leave this workshop knowing how to use Hadoop, and so you absolutely will. And then we can go from there on to more of the bleeding edge kind of things. In particular, probably the most credible technology that's succeeded Hadoop in enabling new and different types of paradigms is Spark. So we'll spend a good bit of time with Spark, although we'll also be able to field lots of questions about other related technologies that will come into play as we talk about this stuff. And the last thing we'll end with today is we'll give you a more in-depth tour of the platform you'll actually be using today, which is Bridges. It's the platform you'll all be logging into and using to do our exercises today, but it is because, well, I'll just jump into the next slide here and show you, because of its nature, it is the first of the really focused big data platforms in the XSEDE computing, the NSF computing universe, and as a consequence, it is a fairly complicated looking machine. It's got lots of different pieces to enable lots of different capabilities. This is different from the machines we typically have in the past and most of the other HPC machines out there in the XSEDE constellation, in that it's not really designed to be a big bunch of copies of small pieces, a big homogeneous looking machine that scales up with your work in a very similar fashion. Instead, this machine's meant to have lots of different capabilities and it's reflected in here, one view of its schematic view of how it's put together, which looks very complicated because it is. It's got lots of different capabilities and pieces. We'll be using some of those pieces here today, and I'll end with a talk about what all the other pieces are and how they relate to big data. So your resources here are your local TAs who can certainly help keep you on track with all kinds of logistical issues, login issues, and connectivity issues, and any questions that you have that are more directed towards a particular expertise we're talking about here today. Please stand up, ask questions. We encourage lots and lots of questions from the audience, and we have time in the agenda to accommodate that. The talks are all online at this point, so you can play along with them in your web browser if you'd like to. And as I just mentioned, XSEDE is what's providing this training here today and what's providing the platform we're using here. And I've become aware after the workshop that a lot of people don't know exactly what XSEDE is, and you absolutely should, because XSEDE exists not just to deliver some one-time training events like this today, but it exists to give you, it's an NSF organization to enable American-based researchers to have access to large platforms to enable scientific computing. So it is not just for training, it is also so that as you outgrow your laptops or your departmental resources for whatever types of high performance computing or computing you're doing, you can move into the high computing performance realm in a seamless way. You can jump onto one of these supercomputers and continue to work with resources that you couldn't possibly get access to otherwise. And it's very easy to get starter grants to continue on these platforms. It's extremely straightforward. It's a trivial application process. If you want to have millions and millions of hours on the biggest machines, it's a much more involved process. You've got to justify your time and everything. But for you to continue after this workshop and use Bridges or other XSEDE platforms is no more than asking for a starter grant. That process is at this link right here. It's very easy and very straightforward. Although I'll take the opportunity now to point out that we're going to allow you to keep your accounts for a little more than a week after the end of this workshop. So we encourage you to continue to do the exercises and play around and kick the tires after the workshop ends. Okay, with that, let's jump into the intro to big data talk here, because this will give us kind of a grounding and an overview of some of the topics, kind of a survey of the topics that we're going to talk about for the rest of the day. But I did promise, actually, before we do that, I promised that we would get a little head start on getting online and getting our hands on access in the event that there is something weird that happens. We like to deal with it in the background so none of you lose any hands-on time. So the one thing, yes, it is up here, the one thing that we want to take a few minutes to do right now is to verify that all of you can access the web-based stuff through our proxy server. So let's take a moment before we start here and make sure that if you do what we have here in, should I get a pointer over there? Yes. If we look on our web page right here, we've given you all instructions for the proxy setup guide here. We've given you all detailed instructions about how to make sure you can access the web-based stuff here today. So you should have all seen this. If you haven't, don't panic. We're going to take a minute now to walk through this. So we've got our proxy setup. We want all of you to step through this and make sure you can do it. The only information you need to do that is that there is a password, a username and a password that all of you will share. It is this one right here, Hadoop Training Today. One big word, all lowercase. So we're going to take a few minutes here to step through this and make sure everybody can do this. So I am going to, let's say, assign 5 minutes to this. It shouldn't take more than that. If there are problems, please let us know. Let your TAs know. They can let us know through our chat channel, and we'll sort anything out. I don't anticipate that. So let's go ahead. We'll take 5 minutes to make sure everybody can do this if you haven't already, and I expect you haven't. So please go ahead and give us a shot. Workshop page that you've all been to at one point or another. So here's the workshop page right here from the psc.edu page. I apologize for these ridiculously big Hadoop generated URLs at the top of the page, but they are what they are. But if you go to the training page, you will see the proxy setup guide right there. So that has the instructions that we should all step through right now. I'll leave that page sitting up, and then you can find the subpage from that more easily. And there's the password. And this is not the same as the password to log on to Bridges. This is to enable all of us to use the web interfaces. It looks like in general everybody's fine. For those of you that really want to test and make sure, because there's really no final step to test there, you can test it by going to this URL right here. Otherwise, we suspect it'll work fine and we can deal with it when we get to hands-on. So I don't want to take time out of our packed agenda here to do testing, but if you want to in the background, go ahead. Instead, let's go ahead and get started with some actual learning here. You are here today to learn about big data techniques. Well, it's probably important to define big data. Unfortunately, that in and of itself is a tricky task. So I would be, let me actually start my presentation here. Ta-da, okay, there we go. I would be remiss if I didn't throw up, at least briefly, everybody's favorite definition in this field of big data, which is this quote from Dan Ariely that's been around since big data has become a big topic here. And it basically conveys the idea that any given definition for big data is sure to upset somebody and exclude some other group because it is such a rapidly growing field and it encompasses so many different technologies and so many different approaches. However, the Wikipedia definition isn't actually too bad. It basically says big data is a broad term for data sets so large or complex that traditional data processing applications are inadequate. Well, that kind of presumes that you know what traditional data processing applications are and techniques, and so let's take a look at those and where they come from. And essentially the idea is that if you can understand that data isn't an abstract concept, but is instead an actual bunch of records sitting out there on a disk system in most cases that you're trying to access in some way, you won't go wrong. You won't get steered wrong by trying to understand what paradigm you're implementing at any point in time. So let's look at the issues that do show up when you're looking for data. If you've got grandma's recipe box out there and she's got it organized by a bunch of index cards in there, and in each one of those sections she's got her appetizers and her entrees and her desserts, then if you want to find a tasty appetizer, it's very easy. Go to the appetizer section and you can browse through. But what happens if instead you've got a bunch of oranges you've got sitting around and you want to use them up, and so you want all the recipes that use oranges? Then it gets a little bit more complicated, right? Now you've got to go through the data manually. And that's the issue with big data. The issue with data is how do you organize your data in anticipation of you needing to access it in some manner. And what we'll find is that modern big data techniques are often going to allow us to use parallel access to the data, raw horsepower, to overcome the need for complex, traditional organizational schemes. So you might think that if we have a little bit more sophistication, if instead of grandma's recipe box we have a nice filing system like you might find in some law office somewhere, that this enables us to kind of get to data more easily. And so if you want to find all of your clients whose names start with A, probably easy to go to the filing cabinet that's got A on it and go through it and you find all your clients. On the other hand, if you want to find all the cases from the year 2007, it's going to be a lot more complicated. Now you're once again faced with going through all of the records to try to find things. Furthermore, if you want to find all the cases from Clinton County in 2007, that's going to be even worse. And so this is kind of the essential idea of accessing data and performance, is that your indexing scheme match your data in some reasonable way. So sometimes less sophisticated is better, and we're going to find that our actual schemas or organizational patterns that we're going to use in big data world are sometimes fairly crude looking. We're going to look at key value stores as our primary way of accessing data today. I'll define that in just a moment here. But less sophisticated is sometimes better. For example, if you go into my office and look at stacks and stacks of papers, you might find that magically I can find articles from the year 2007 because I just go down some of the stacks until I start hitting that layer around 2007, and that's most of the stuff that's hanging out in that layer is going to be from that year. On the other hand, not too good if I want to find all the articles in my office on fault tolerance. So your scheme that you organize your data by is going to give you the payoff in the end when you start trying to look at things. Now, how to handle big and complicated data in ways that allow us to access it with multiple types of queries and complicated queries is not something that's brand new. It's not something that big data brings along with it. As a matter of fact, we'll see that complicated queries are something that traditional databases handle, SQL type databases handle very well. But it's not even something that comes along with the world of electronic databases. If you go into any library sophisticated library, you've always been able to say, find all the books on modern physics, and because there's a Dewey Decimal System says that that's all the things that are in section 539. If you want to find all the books by Wheeler, that's no problem either. You go to the card catalog, and things are cross-referenced there by author. On the other hand, these things eventually break down when you want to start doing things like find all the books where Wheeler isn't the first author. So he's not the one that's listed in the card catalog. It gets to be tricky. And so before we launch into how we actually do these things in modern databases, the whole library thing here brings up the fact that people like to define big data by some size, some threshold, where how many bytes do you have sitting in a file starts to determine whether it's big data or not. And that's not really fair. It's not a good way to look at data. It's a very one-dimensional way when data has other characteristics that can make it big or complex as well. But somehow or other, over the past 10 years, kind of an official unit of big data has been how many libraries of Congress is your data set, which somebody somewhere along the line came up with a very silly and inaccurate definition. The Library of Congress is about 10 terabytes of data. Now that's not actually true. The original reference everybody cites for that actually said that the Library of Congress probably had about 208 terabytes of data at that point in time in text. The digital collection alone is now many petabytes of data, but nevertheless, this has become some kind of threshold or for when things are big data, is terabytes of data. And again, that's it's a very relative term, and a better way to think of big data is not just size, but also the way things are organized, or these days with big data making its way into lots of online enterprise applications, it's also throughput at times. How well can you stream data through a system? So I'll just pull up some biggish sets right here so you get some idea of what we're talking about. And the size one is these days hundreds of terabytes are pretty large data sets. And that shouldn't surprise you given that you can buy 8 terabyte hard drives off of Amazon, right? So a big one is, for example, the 1,000 Genomes Project. Amazon hosts that at their site, for example. It's 260 terabytes. More interesting, I think, are the other ways of looking at data, which is, for example, throughput. Probably the most stunningly awesome data set in terms of throughput is the Square Kilometer Array Radio Telescope, which is being deployed right now. And when it's fully deployed, it's going to generate an exabyte of raw data daily from this antenna array and all the signal data that it's catching. And that's going to be compressed to actually store it and process it down to 10 petabytes a day of data. So that's big data in terms of how fast you're generating it. Can you possibly consume it and analyze it in an appropriate way? Another way to look at big data, and one that probably is going to be more interesting to us in this workshop, is in terms of how many records and how complex is the structure of your data set. And GDELT is a data set hosted by Google. It's their global database of events, language, and tone. It's a database that encompasses lots of newsworthy type of events so that researchers can analyze the interrelationship between things that are happening in the world. And it's an example of a database that's very complicated in terms of the number of fields that it has, or the number of distinct types of categories that it's trying to encompass, because it's up to 59 fields, probably more actually, 59 fields when last I queried it, 250 million rows, so 250 million events. Each one of those events could be up to 59 different types of fields, characteristics, and that field number is growing constantly, and it's very adaptable and flexible. And that is representative of kind of, well, we'll look at in just a moment here, big table-based store. This last one is also representative of one of the characteristics of big data sets, which is they're a little bit less rigorous. The performance in accessing them, as well as the maintenance of these data sets, is a little less rigorous than a traditional data set coming out of, say, a bank somewhere, where your bank account, you hope every single byte of that bank account, every bit of that bank account is well accounted for, and you know exactly where every number that's generating your statement is coming from. You'd be disappointed if your bank wasn't that diligent. On the other hand, a lot of big data sets like this one right here might vary from one query to the next a little bit. And that should shock no one in the age of Google, when if you issue a Google search, which means essentially you're going through Google's index of web pages to look for a topic, and then a minute later you did this very same Google search, if that page looked a little bit different, if some of the entries were a little bit different, you certainly wouldn't be stunned. you'd say, it's, it's doing a lot of kind of stuff out there, random, pseudo-random, and non-deterministic things are going on in the background. I'm not amazed that my Google search varied from one iteration to the next. On the other hand, you would be very dismayed if your bank account varied from one look at the ATM to 2 minutes later at the ATM, and it varied for reasons that you couldn't figure out. So that's a characteristic of modern big data sets, and we'll see some of the reasons for that. Way of organizing data. This is the way that the computer science, the business world has been doing data organization since the 50s, and we'll look at what that is exactly. I'm not assuming that you guys are proficient or know about that, but it's still important. It hasn't been become irrelevant to look at data in well-structured and well-understood ways just because we have new, more free-flowing techniques. And a lot of those techniques are gathered in the category of NoSQL, NoSQL type technologies. And these are the ones that I'll step through them here, give you at least a quick overview of each one of them right here, and then we'll look at some of these in more depth today, and we'll see how they're enabled by things like Hadoop and Spark. The last category is one that's kind of emerged out of these capabilities, the ability to do new and different things with big data, which is big data analytics and machine learning. And this is a topic that deserves an entire day to itself. As I said, I'm sorely tempted to expand this to 2 days, mostly to encompass a lot of these kind of things. But these are related very much to big data because they're not meaningful without big data, and we'll look at them a little bit as well. So let's start at the beginning, as it were, with good old SQL. And these are all the classic databases, the Oracle database that might run your school's enrollment system or pay system, the Postgres or MySQL databases that are used for any kind of classic, hey, here's a bunch of records I need to keep track of on the computer kind of things. And they revolve around tables of data that are very well structured, that you, as the implementer of the database, have a very good handle on what kind of data you need to have organized, what the relationships between the data are, and what kind of questions the user is going to be asking in the end. And you do these queries with what look like some pretty English-looking statements that say select table and grab some data from it, maybe combine it with some data from other tables. And it's fairly straightforward. It's not a difficult or sexy technology these days. So why isn't it fashionable? Why don't we just use this for everything? And why does big data involve all these things that are NoSQL? Well, one of the reasons is that the schema or the organization is pretty much set in stone with these databases. You really don't just play it by ear and add new fields and new tables into the databases. In general, you hope instead that from the initial architecture, you've kind of captured most of the use cases and most of the data that you're going to incorporate into it. And sure, you can incrementally add things that people do, but it's not the intent. The intent is not that every week you come in and add a new field in or a new table in. So they're not as agile in terms of incorporating new and exciting types of data that your new sensor on your drone is capturing all of a sudden, completely different types of data. Or your web page now is asking users for totally different information than it was in the past. SQL is not great at dealing with that kind of stuff. Queries to the database often require the statements that you do issue, SQL queries that you do create, very often require it to go from one table to the next hunting for data. If you have a table that's organized with your employees and their addresses, and then you have another table somewhere that's got their, say, their pay, and you need to figure out the taxes that you should collect based on the county that they each live in, it has to start going from one table to the next for each employee. And hopping around those tables, hopping around things that are stored all over different disk systems can be expensive. And so making these queries and combining data on these things, joins essentially, can be very expensive and low performance. Another thing is that sharding, or breaking these things up and distributing them across parallel file systems, which these days parallel file systems are kind of the norm. Many of you out there might have raided file systems right on your desktop, and certainly any of you that are storing anything in the cloud out there, what's happening is that the data that you're dumping out there is being broken up into pieces and distributed across many disks, and that's for primarily two reasons, one of which is performance. The data is now spread out and can be accessed simultaneously, pieces of it at one time, instead of it having to load in things sequentially. Also for reliability. You can have things that are duplicated, either just completely redundantly, mirrored, or maybe in some more sophisticated fashion, where they've got some kind of error correction scheme. But at any rate, breaking things up and putting them in pieces all over the place is common and a very effective technique. But with structured tables of data, it's not all that obvious how you can start breaking up these tables and just randomly throwing them out there on the disk system in real time. You can do it, but it's not just a matter of just, hey, here's a new record, just stick it on a different disk drive than the last record that came in some round-robin scheme. For some of the other techniques we'll talk about, a round-robin or a hashing-based scheme will work just great. This last one up here, though, this last point is probably the main reason for performance that SQL is just not acceptable for a lot of these applications, and that is that SQL has a lot of guarantees about exactly the way data is written and read that are fantastic if you're, as I imply right here, a bank. You hope that your bank has very deterministic results for storing data and retrieving data. You hope that if I'm at an ATM putting in a deposit and a clerk somewhere in a back office is also putting in your paycheck, you hope that both of them accessing that record at the same time can't make something weird happen and all of a sudden, boom, all of your money just disappeared because people didn't really think through what happens if they're both trying to enter values in the same place. Instead, classic databases are very, very focused on making sure that those kind of collisions can never happen and result in bad things. They have all kinds of journaling techniques and everything to make sure that independent accesses to the same point don't do bad things. They have all kinds of backups to make sure that values can't exceed certain things and triggers do other things. And all of that stuff rolled together is very well defined. As a matter of fact, one way of defining things to make sure that they work in a very, very specified way are ACID consistencies or ACID specifications, and this guarantees us that, again, collisions won't happen. It also guarantees us some other things with regards to durability and whatnot anytime you're transacting with the database. And you might say, okay, of course, that's a great thing. Why wouldn't all databases do it? The answer is that it's very costly to cover all of those cases. Covering all of those corner cases is something, again, your bank has to do. On the other hand, Google is searching for a web page because you want to see, what are your options for trying to buy knitting supplies. They don't quite care so much that they might leave out occasionally 1 out of 1,000 of the possible search results. It's just not an issue for them. It's not something that they're going to sacrifice all this performance for. And so these ACID consistencies are very, very costly. They also inhibit, one of the reasons they're costly is they inhibit caching, or the ability to distribute data around the system. Caching is a very effective technique for improving performance in all kinds of areas, not just with data, but with all kinds of things. The ability to say, hey, keep a local copy of some data instead of always going back to the central source for the data. That local copy can make things a lot faster. So Google has their databases spread out all over the place. When I'm accessing, going to Google search, for example, I might be pulling stuff off of one of their data centers here on the East Coast. The next time I access it, because the East Coast data center is busy, maybe it goes to the West Coast, and maybe that data is a little bit different on the West Coast. It's not synced the same. Who cares? Well, again, with your bank, they very much care that there is one copy of the data. So the kind of guarantees that a classic database give you are very expensive. So I hope I've given you some of that reason, because the rest of the day is us going to be seeing how, if we relax some of these constraints, we can get a lot more flexibility and a lot more performance. So that takes us into the world of NoSQL, NoSQL, which, what does that mean? Does that mean everything else, or does it mean not only SQL? For a while, it was effectively no ACID, databases that don't have these guarantees, these consistency guarantees I just mentioned. Nowadays, it probably means mostly not databases that aren't relational databases, classic relational databases. So the term is a little bit blurry, but when you hear it, and you will hear it in big data, it's basically saying, okay, we've moved on from the classic database with all the guarantees it gives us. So let's look at kind of the opposite of a big, complicated, table-based database, a key value store. This is kind of the simplest version of database, and yet, as simple as this is, you might think this is a toy example I'm giving you here just to kind of start out our progression as we march towards more complex databases in the NoSQL world. No, actually, key value stores are a very dominant way of accessing data, and we'll see how something that seems so simple can still be very effective. But a key value store is the exact opposite of complicated tables and well thought out schemas. Instead, a key value store says we just have a bunch of data sitting out there of some perhaps completely unknown format, but we can get chunks of it just by asking for the key. We give it a key and say go retrieve that chunk of data. So a key value store says, as I've got a table up here on one side, we've got keys. The key might be foo, a word. It might be a number. It can be all kinds of different things. It's not always just some well-organized index. It's not 0, 1, 2, 3. A key can be a very complicated string of stuff. And when you give the key to the database, it comes back with some chunk of data of some unknown format or type. Now, this is certainly a very agile way of setting up a database. If we get some more data in, we don't care what's in that data. All we need to do is make sure we've got a unique key to access it by, and we stick it on the end of our database. It's certainly scalable in the sense that, again, all that new data coming in, we just stick it on the end of the database. Oops, we're out of space. Well, let's buy another disk drive, stick it in our system, and start loading data onto that disk drive. As long as we can get to that key and that new data on that new disk drive, it's all good. As opposed to, you can imagine well-organized tables where we just bought a bunch of new disk drives. How do we now expand our tables onto those new storage systems? A good hashing system, in other words, a good system to take a key and just determine where does that key belong, which disk drive. If I've got thousands of disk drives out there, as long as I have a way of taking my key and saying, how does the key point to a disk drive, then I'm going to have a pretty efficient system. So that hashing is a big part of the performance for all of these systems. And hashes are pretty well understood formulas for, again, going from a key, which might be a complicated string, to saying where is the data likely to reside out there in some kind of ordering. Sharding and backup could be very simple with a key value store, right? Sharding or breaking up our data into new pieces is a matter of just, again, our new disk drives arrived out there, we can just start loading data onto them. And backup, now all of a sudden backing up any of those disk drives, we can just take and start duplicating the data somewhere. As long as our hashing can point to that new backup as well, we're good to go. So it's a lot easier than trying to keep well-organized tables. But this last one I've already alluded to here, which is that this last bullet up here, which is our keys, are not typically going to just be, again, an index like a 0, 1, 2, 3. They're going to be complicated strings. And the reason for that is that sometimes that makes a whole lot of sense in terms of how you're organizing your data. For example, key value stores are used in lots of online databases to enable, say, transactions on a shopping-based website. And we might be on Amazon, and your shopping cart on Amazon has a bunch of stuff in it at any point in time, and it's changing rapidly as you add things to your cart or delete them from your cart and buy stuff. And so the key to get to your cart can actually be a complicated string like I've got right here that says it's got your username in it and it's got the last timestamp of when you accessed the cart. And so the key itself can have a lot of information embedded in it. And then all I need to do to go and find your current version of the cart is I type get and then that cart string, and it goes out and it grabs your current shopping cart. And so very simple scheme, and yet if your keys are clever and have a lot of information in them, you can accomplish a whole lot in a way that's very efficient. Now, you might say, okay, well, those chunks of data that come back from my key value store, or if you're Amazon, you might have some weird bunch of, you might have some binary format and everything, but it's your database and you know how to parse it and it's all good. Or you might have a very simple requirement. It might always be a text string. It might always be a picture, and that's good too. On the other hand, you might actually have your key accessing a complicated document that's got a bunch of different information in it because it needs to be some employee record with all kinds of information, fields, and photograph of the employee and all that kind of stuff, in which case you really want a document store. You want that value to be something that the database itself understands. What makes something a document is that the database can actually peer into that value and start to extract some information. So it actually has some well-defined objects. So for example, you can issue queries to the database to say, get all the plants that are daisies out of the database, and it can go through and look into those values and figure out which ones have a plant field in them and that it's equal to Daisy. So that means you have to have some well-defined format for the documents that you're storing. Common ones are XML, more commonly JSON, that's misspelled right there. It should be spelled like the second one there. Binary JSON, and nested versions of these. So there are some well-defined formats out there that kind of are meant to be self-explanatory and self-documenting that are common in this field. And we'll talk more about these and where they show up today as we go through things. Which means your queries can now be quite complex. So you can actually issue some really complicated queries that combine and go through the document and do different operations. And LINQ is a common way to do that in the Microsoft side of the world, LINQ type queries, JavaScript functions that can go and look through the document and come up with any kind of results you want. Different databases, and I've listed some of them here, Cassandra and CouchDB and MongoDB, have different ways of storing and organizing all these things. So they have very different performance characteristics, so not all the same. They each apply to things in different ways. Now, this is not an object store. So there are databases, I think these are a lot less popular these days. For a while there, the attempt to move off of strictly relational databases with object-based databases, and the objects have these self-explanatory and self-documenting and self-accessing kind of functions and whatnot. This is not that. Instead, what you have here are documents that are a very clearly defined format. It's some kind of XML or JSON or whatever format. So they're not object stores. We won't even talk about those. So here's an example right here. I mean, here's where your key grabs you back a document that does have some organized format. The format can be some nested thing that's very complex and has some incredibly deep amount of information, and that's not uncommon, but it's at least well defined in advance. Now, something that's not so well defined in advance, gives you a lot of flexibility, are wide column stores. These are things that have become quite popular with lots of big online cloud-based type databases. Google Bigtable is an example I mentioned earlier for the GDELT database. Cassandra, HBase also are set up this way, which is where they look like they're tables of data. So they look a little bit like a classic SQL big table of data. The difference is that the fields themselves can vary, and they can vary from one row to the next, and they typically do. That's the reason we're using this. Classic SQL table, everything's defined in advance. If this is the user, then we've got his email, then we've got his address, and that's the way the table looks for everybody. In a wide column store, instead, each column, each row can have different columns. And even if so basically one way you can think of this is it's actually a 2D key value store. You give it a key and then it returns something which also has a bunch of keys to return different fields within it. So every time you retrieve a row, now you can also look within that row for varying numbers of different things. So it's, again, you can think of it as a 2D key value store. Different databases, so there are variations of these out there, Bigtable, Cassandra, HBase. They also aggregate and store things with different patterns and in different ways, so they can have different performance depending on the way that data is organized for you. How much do you need to access the data versus how much do you need to create new fields? These are the kind of things that can make you prefer one over another. But all of them have this characteristic that they're very dynamically defined tables. A very different type of database is a graph-based database, where you're more concerned about the relationships between the data than you are about organizing things in some tables or just heaping the data out there with some information attached to each key. With a graphical database, you're very much concerned about, again, the relationships like you might find on the web. So the semantic web, or the ability to mine the web for relationships and data that's out there, is a very interesting and dynamic and fast-growing area where graphs are the key way of organizing things. Any algorithm where you've got graphs, anybody that's taken computer science, 101 kind of things, you know graphs are a very common data structure to find in any kind of program. And anytime you find yourself in a program where everything's organized by a graph, it can be very frustrating to figure out how to serialize that stuff or turn it into something that's not a graph. Well, graph databases allow you to keep that. So anytime you've got some algorithm that's doing 6 Degrees of Kevin Bacon. You know, what are the relationships between actors in movies? And that's the way your algorithm is. Well, Graph Database allows you to work with that in a database instead of trying to figure out how to turn that into some flat structure. So it's great. I say this jokingly here. It's great for graphs, but it's not jokingly in the sense that many of you, if not most of you, surely have encountered graph-based linked list data structures in things that you've done, algorithms that you've done. Well, that's when you pull in a graph database. Now, the difficulties with graph databases are they can be very hard to visualize. As a matter of fact, here is the web page, the splash page for the PDX Graph Meetup group. It's kind of an online community dealing with graph databases and whatnot. Here's their splash page, which they I'm sure perceive this as a very impressive graphic, visualizing some complex graph relationships, and indeed it is. You can also perceive it as indicative of how difficult it can be to visualize the relationships in graph databases. You know, when you've got things linked to other things, it can be very difficult to disentangle that in some way that's obviously meaningful or intuitively meaningful. Serialization, ultimately when you do have to do this in some non-graph version, if you've got to pipe things over the web or turn them into a more traditional database, can be a difficult issue. It's not a given how you turn graphs into non-graph things. The queries can be more complicated, but they're certainly different. And they give you different capabilities, but they require you to think differently. These days, the kind of queries that you issue through databases are pretty well standardized. There's a World Wide Web Consortium standard called SPARQL. And this has it has kind of a very well-defined way of looking at everything as a triple. Everything in the graph is a triple, and everything stored as triples. And you can define schemas or overall relationships between things. And then at the end of the day, you've got something that looks kind of like SQL queries, but instead allows you to look at graphical relationships between things. It allows you to pull up stuff from the database based on its relationship. And SPARQL's been around for a while. Again, it's a World Wide Web Consortium standard, but it lacked a few things that the Neo4j database or structured query or query language Cypher had, and for a while it was proprietary, and so there was this tension: do I use proprietary thing or do I use the more standardized thing? However, Neo4j is now no longer proprietary, and it has some additional capabilities. It can store a whole graph, not just these tuples, these list of triple things. It allows for named graphs, in other words, for you to distinguish between sections of graphs and relationships between graphs themselves. And it also allows, maybe this is the biggest difference here, it allows for one way of defining as property graphs, which is essentially a way of saying that the edges, the connections between the graph, the nodes, also have values. And that can be very, very helpful in all kinds of graphical relationships to have essentially weights between the edges, on the edges. And SPARQL is kind of limited in that. Neo4j has always accommodated that very well. And again, both of them end up allowing you to interface with your graphical database via something that looks like nice SQL type queries, but instead has the ability to say, hey, how many actors are within 6 movies of 6 Degrees of Kevin Bacon? I'm assuming all of you know what that is, where how many you try to figure out, link any given actor to a Kevin Bacon movie by looking at actors that have shared roles in other intervening movies. That's the kind of thing you can extract out of a graph database. As a matter of fact, that's a classic application that people do, toy problem. Not so toy problem that people do, because the online movie database is out there begging you to do that. So graph databases are, again, a very different type of database that we find more and more of in the world of big data. So all of you here today, though, know that a big part of our agenda is Hadoop and Spark. So what kind of databases are they? And the answer is they are not databases. Hadoop and Spark in and of themselves are not databases at all. Instead, they are frameworks that you can build databases, big databases on top of. What they do is they give us the ability to do a lot of what we've been talking about so far, but in parallel. And this is the key. This is really the thing that enabled the big data to emerge as an interesting field, and it is the key concept for you to think of in terms of everything you're going to learn today with Spark and Hadoop, which is that I mentioned to you earlier the difficulty in searching for a library book if it's not indexed just right. Well, big data, Hadoop first, now Spark and other things in the big data world, and that enable us to kind of cheat in these searches, because instead of just sending out one librarian to find all of the books where Wheeler is not the first author. So we can't find all the books where Wheeler's the author. Well, we can find the ones where he's the primary author in our card catalog, no problem. But the ones where he's not the first listed author, well, what are we going to do? Go down all the books on the shelf and search? And the answer is yes. If we have enough librarians, instead of just sending one lonely librarian out there to look through all the books, if we have hundreds of librarians, then they can go down the shelf and they can look at all the books and say, oh, there's where Wheeler is the second or third author, and they can bring us back all the books that Wheeler is the author of because they're doing it in parallel. And so this is the big breakthrough that enables big data, is the ability to do things in parallel. We'll find that our databases, once we distributed them over a bunch of different disks, which I've already mentioned is an obvious thing to do, what if we found ourselves where all of those different disk systems had computers attached to them too? Turns out that that's pretty much a natural thing to happen when you build data centers. Each one of your disk systems out there is attached to got some blade attached to it that can access those disks. You got all this computing power out there. Why don't we have all those computers start looking through the data simultaneously? That, which becomes Hadoop, which you'll look at very specifically and you'll understand exactly how it works, enables us to do lots of things that we couldn't possibly do otherwise with these otherwise primitive-looking key value store databases and things that don't have all these nice indices built into them. So that's what we're going to do here today with Hadoop. Now, Hadoop then allows us to build on top of it. HBase, for example, which looks a lot like a SQL kind of database, or Hive, which actually Hive looks very much like an SQL type of database. HBase is more like a big table type database. With Spark, which we'll get into, that framework, which then brings in even more modern approach to computing by saying, hey, we have the computer, we also have a lot of memory on these computers, can we do things in memory as well? That allows us to do things like Spark SQL, which gives us a very SQL type interface, old school SQL type interface, to a big enormous pile of data that's not actually organized in SQL tables. It allows us to do graph databases and allows us to do machine learning type approaches here with mlib, which is a component we'll talk briefly about, where we can do very complex analyses of the data in place. But all of these things are basically enabled by the fact that we now have an army of librarians instead of one librarian. That's the key concept, it's the key capability that upon its arrival on the scene allowed these things to happen. So with that as the end of our overview, we're going to get you guys into actually doing this stuff. So the next thing here is Brian's going to lead you into Hadoop to actually start doing some of these queries on an actual distributed file system. So I will be glad to answer any questions that we have here while we flip over to Brian here. And let's see here. We are more or less, I just lost my clock here. I think we're more or less on schedule here. We're close enough. And okay, well, let's go ahead. We'll flip laptops. Again, if you have any questions out there, I realize it was kind of fluffy intro material, but if you have any questions, go ahead and ask them now while we're switching ourselves over.
Sorry, I didn't quite understand what is this triple store.
Triple store format? Okay, well, with graph databases, one of the key relationship you have is actually the relationship is defined with most triple stores as subject, verb, object, subject, predicate, object, where you've got actually you're saying everything. I'm making this more common. I'm introducing definitions where I don't need to. It's simply a node connects two things, right? A node connects from here to there with some relationship in between. So if you define a graph as two things related by something else, then you can imagine you can store all those relationships always as a triple, as three things. Here's one thing, here's how it's related to another thing. So, and the metaphor I was jumping into, because the technical terms are, it's like an English sentence where you've got subject, object, verb, this relates to that. Car is red. Joe is scientist. So you can break the whole world down. The idea is we can break the whole world down into a bunch of triples and store everything as a bunch of triples, and at the end of the day, those turn into graphs, how everything is related to everything else. So that's kind of the key concept of triple stores, and that's what RDF and whatnot is built on. Okay, you want the wire, or are you good? Wireless. Okay, you want to get it. And
we haven't had people connect in via SSH to currently, right?
No, we did not.
Okay, we'll do that. I guess when we get to examples.
Okay, well, hello out there. My name is Brian Gill, and I'm the Hadoop administrator here at the PSC. I've been working with Hadoop since the 0.14 edition. We're on 2.7 point something now, and that's back in the aughts really. So it's starting to be a while. Back then, if I had asked you, have you ever heard of Hadoop? Almost certainly the answer would have been no. But these days, it's a lot more common. But still, a lot of people don't know a lot about it, so we're going to get into some of the details of just what Hadoop is and how it works. So what we're going to discuss today, we're going to talk about the architecture of Hadoop, and we're going to talk about the classic MapReduce approach to solving your big data problems versus the current Yarn platform, which was introduced as a sort of an overlay to MapReduce, and it was thought that this would allow different kinds of applications to be built on that, and you'll see that that was a mixed success. We're going to talk about Hadoop streaming, which is a really nice feature of Hadoop, which allows you to write in any language that you like instead of just using Java, which is the native language that Hadoop was written in. And we're also going to talk a little bit about some of the other applications that live on top of the Hadoop file system and ecosystem, such as Spark, which John's going to talk about in a little bit more detail, HBase, which is a very common database, and some other applications. We're going to go into depth mostly with just writing a simple Hadoop application. So let's talk about what Hadoop is. Hadoop is a framework for big data. John went into some degree of detail about how we define big data, but for our purposes, it's enough to say that it's just data that's too big to be handled by standard tools. So when you scale to the point that you're starting to run into limitations with your existing rig, then you move up to using Hadoop to do processing on your very, very large, sometimes multi-terabyte or even bigger data sets. And typically, this is something that an appropriate job for a Hadoop cluster would be something that's processed on thousands of nodes and takes up a great deal of space. There are a lot of cases where people will want to use the system just for the ecosystem as opposed to because they have actually reached the point where their data is big enough that they can't do it any other way. However, this is the impetus behind it, and that's what drives the design of the system. Let's talk about the MapReduce algorithm briefly. This is kind of the heart of Hadoop. Hadoop is a system for applying some very simple, at least in theory, functions to a very large amount of data all at the same time. Just almost extreme, almost completely horizontal, perfect linear scaling is the idea that they're going for. The idea is that for all of the key and value pairs in your data, which is how Hadoop asks that you organize your data, you apply a function to that pair, which can be done on any of the nodes, and then you gather them together and sort them, and then you reduce them, have a separate function that aggregates all of that information into a digestible output, which is the conclusion of your application. I've got the link here to the original paper, which was published back in 2004. It was a Google idea initially to create a big data system like this. MapReduce on its own is not really a new idea, but applying it in this way to simplify the processing of very, very large data really started with this paper back in 2004. And then a guy named Doug Cutting at Yahoo created an open source implementation of it, which eventually became the Apache Project's Hadoop. And if you've ever wondered where the name came from or why the logo for Hadoop is an elephant, he named the system after his daughter's stuffed elephant. So I think that's cute. Okay, so in addition to the MapReduce system, which is the canonical way of interacting with your data within a Hadoop system, Hadoop has become perhaps even more famous as simply a platform for other big data applications. And again, John went into some detail about this with Spark, Hive, HBase, and there are some other newer ones like OpenTSDB and Metron that we've used here, and just anything you can think of, you name it. And part of the appeal of that is that the system is split into two parts. There's the HDFS, which is the Hadoop Distributed File System, which is a very effective distributed file system for storing your data that a lot of applications take advantage of without ever touching the processing application part of it, which is the MapReduce system, or historically was the MapReduce system, and now is the YARN system, which stands for Yet Another Resource Negotiator. You won't need to know too much about this split, but you do need to understand that the reason that a lot of applications use this is because they actually just directly interact with the HDFS and ignore the processing end of it. Okay, let's talk about how MapReduce works. We apply a function to all the data. That's the map end of it. And then we harvest, sort, and process the output. And I have a little shell command here, or a series of shell commands. Cat, grep, and word count-l is what those are, if you're not familiar with the terminology. In principle, at a very large scale, all that a Hadoop cluster is doing is something very much like this. You're catting or typing out all of your data. You're applying a filter of some kind to it, or some transformation like a grep. And then at the end, you'll take all of the output and do something useful with it. For instance, count the number of lines that matched your rep, for instance. So this is a map of your data and then a reduction of your data. In a Hadoop system, you're going to be doing something very simple, very similar, just again on a much larger scale. Or if you want to, you can actually use these commands, as we'll see. Okay, here's a diagram that displays just a little bit of how the Hadoop system approaches the MapReduce system. So we start with our big data over here. It splits it in order to process it into, in order to process it on the many nodes in the system. Typically, this is done by default on 128 megabyte blocks of your data, but depending on your input format, it can change, and we'll talk a little bit about that. You apply the map function to each split of your data, and then you get your output, which is sorted. And then it's all funneled back into the reduce phase, and this can be a little bit misleading because it looks as though we're funneling back into a single reducer, and that the reducer makes everything smaller. Those things are not necessarily true, and in fact it's typical that you'll have more than one actual reducer aggregating some portion of the output into your final output. Reducer meaning a node dedicated to this task. And also, it's not the case necessarily that reduce has to shrink your data. You could actually have a reducer that simply echoes back what you got or even expands it in some way. The sky's the limit really as far as what you want your program to do. This is canonically the way that people typically approach the MapReduce applications. Okay, let's talk about the HDFS aspect of Hadoop for a moment. So this is a distributed file system layer. It lives on top of the other file systems, so you might have, say, an ext3 file system and on each of your nodes, and this lives in files that live in that file system, but they appear as a single coherent file system to the Hadoop cluster. And the metadata is all kept in a head node, which is known as the name node. The HDFS file system is a write once, read many file system, and it is optimized for streaming throughput. So the idea is that, as John alluded to, this is not a great solution for something like a bank database where you're going to be making lots of small changes to a very intricate database. Instead, this is a system that's designed really for streaming as much data through your system as possible, as quickly as possible, and not making fiddly little changes all the time with tiny bits of data. This file system also leaves out some quite a few of the POSIX standards for how you would interact with files, in particular editing files in place. There are exports available in many distributions of Hadoop, and I should take just a moment to mention also that we're going to use the vanilla Apache Hadoop, but there are quite a few vendors that provide their own Hadoop implementations and that provide normal POSIX system or fused mounts for the data, but we're going to approach this through the canonical way of accessing the data, which I'll show you in a minute. But it's possible to export your file system so that it looks like, and for the most part acts like, a regular file system from the node that you're going to work from. One of the features that HDFS offers is replication, and this serves two purposes. So each file by default will be replicated 3 times, or rather each block will be replicated 3 times, and as a result each file will be throughout the cluster on different nodes, and in fact to the extent that it's possible on different racks, should you have enough of those so that if you have a major failure you don't lose any of your data. The reasons for this, again, are twofold. The first is for the robustness and security of your files so that you don't lose any information if you lose a node. In fact, the system is very good at continuing on just fine with one node or even a whole bunch of, up to the default number of replication minus 1 nodes missing from your system. But the other advantage of this is that it allows you to process your data in place. So the advantage of distributing a very large data set like this is that you can send the worker nodes, you can have them announce, well, I have this piece of the data, so I'm going to work on it, and you can work out an optimal arrangement rather where each data node or worker node within the cluster works on the bits of data that they already have. So you don't have at the beginning of each job this process of sending a very large amount of data out to each node in order to get things started. Instead, you already have things in place, and only if you have a situation where the same files are on the same node, sometimes you might distribute a little bit of it so that you have a nice spread of your data. But that's all handled behind the scenes within the HDFS. And this is really the big advantage of the HDFS and of Hadoop, which is that when you have a very large data set like this, the traditional way of doing things is to stage your data in and to do some work on it and then pull it back out, and that can introduce a great deal of overhead. But when you have a Hadoop cluster, typically you'll leave your data in place and not only not have to stage it in, but in fact not even have to copy it to the node where the work is actually going to happen. Instead, you do the work where the data already is, and you don't waste any time with file transfers in and out to start and end. Okay, we're going to talk about just a couple of the invocations for getting Hadoop in and out, or data in and out of the Hadoop file system. So this works a little bit like FTP if you're familiar with it. This is the sort of the standard Hadoop way of getting files in and out of your system, and we're going to go through some examples of this later when we get logged into the node and we do our hands-on. But the commands are HDFS. You can also do Hadoop as the binary for this, which is more typically what I would do. DFS, which stands for distributed file system, so it tells it what class of commands to expect. And then -ls is like ls, it just lists the contents of the directory. -put puts a file into place. -get will get one. RM, these are very similar to the Unix shell commands. If you're not familiar, RM is remove, makedir makes a directory, and rmdir will remove a directory. There's also a flag for recursive removes, and there's extensive help for all of these. But these are the basic commands that you use to interact with files. There's another way of doing it which uses the web interface, which we'll talk about a little bit later. Okay, so now we are at the point where we're going to talk a little bit about writing a Hadoop program. And then we're going to get everybody logged in so that we can have you follow along. But first I want to walk you through the text of this program and show you what's in it. So a Hadoop program is going to have a map class and a reduce class.
A comment.
Yes.
HDFS on bridges shows command not found.
Okay, right. So we're not at the point where we can follow along yet, but maybe this is a good time to get everybody connected. So, yeah, so if you are logged in via SSH to bridges, there is one further step you're going to have to take in order to connect up and be able to run these commands. And you can follow me here. Okay, so if you're on one of the login nodes, you just type SSH R741, and that's going to connect you to the node where we're doing our work. Okay, let me know if people have trouble logging in. I'm going to give everyone a moment to get connected up. Yeah. So I guess I should say a word about how this cluster is set up too while we're doing this. We set up special reservations for users who'd like to use Hadoop on the Bridges cluster, and this one is an 11-node cluster right now with one name node and 10 worker nodes. R741 is the head node, and from this node you can do all of the command line actions that we've been talking about. The
Excuse me, this is the University of Delaware.
Yes.
When we type the SSH R741 as you did, it's asking for a password.
Yeah.
And we're unable to connect with the password that we're supposed to use, we believe. Is there a separate password?
There's not a separate password. Are you guys able to get logged in? You guys were. You were
It should
not.
be the PSE username password.
Yeah, so not the proxy password, I hope that helps, but your normal login, the same way you logged into Bridges in the first place. The same
I
username
believe
and
that's
password.
what we've been using. I believe that's what we all tried, and it's denying it says user Schwartz A, for example, has no active jobs on this node.
Oh,
Connection
okay.
closed. Access denied.
They were getting that from Youngstown too.
Okay. All right, I thought that we had that worked out, but that's going to keep everyone, I think, being able to connect. Okay, yeah, I believe that most of you are going to have an issue logging in. Give me just a moment so we can try to address this.
It up here, right? So
Yeah.
I got it. Yeah. When he said to get to the, that's when he said to get to this. Yeah, sure. But what you're saying, you have to go to another node. Yeah. You have to go to the R741 head.
I think I have connected into the account.
The R741 node?
As far as the proxy, did you guys go, which method did you use, or did anybody
You got this
follow the
way.
proxy instructions?
I went through Firefox and I got a test sample to work.
Sure, but then he said that once you're on the Bridges
Okay.
system, you have to SSH.
Yeah.
With
into
Firefox,
the
I know that I tried it the last time with a number of, I was able to get it with Firefox, I had trouble with Chrome. Did anybody else set up the proxy?
I set up with Chrome.
You set it up with Chrome and you didn't have a problem?
No,
Okay.
I set up with Chrome.
Is that Delaware? We still hear you? You want to mute?
Oh. I'm sorry.
Thanks.
Yeah.
I think
Yes.
this was the closest one.
Yeah. I've seen these like elsewhere. Which I've also like seen that you can like just log in and do it. But I think that physically you really have to have actual use. You know, sort of
I think
I'm not sure.
Should be here.
Yeah.
Or you should take permission from that person. That guy could give you the link.
Yeah. I mean, it was only an hour and a half drive. You know, I mean, all things considered, it's easier. You know. Yeah. Drew. Yeah. Nice to meet you.
Yeah, I mean, yeah.
You're on.
Sounds like somebody that needs to mute out there. Please mute your audio, thanks.
Yeah.
Is it UD?
Yeah, UD.
Okay, and that's set up on all of the nodes?
4152.
Thanks.
Awesome,
It'll
thank you.
propagate to every node.
Okay, we can try this again. Apologies for the delay. We had a security change that it's the first time we've tried to do any trendings like this with more than one person on these nodes since we made it. So thank you for hanging in there, and we're ready to get back to work here. So again, if you have not already SSH to Bridges, then go ahead and do that now. And if you are already on the Bridges login node, the command to connect to the head node of the Hadoop cluster is SSH space R741. And it'll ask you for your PSC password, your PSC username and password. And when you enter that, you should be able to connect. And it should look something like this. And then once you're there, you'll find that in each of your home directories, you should find a directory called Hadoop Training 080916. You can go ahead and CD into that. This has some of the files that we're going to be looking at today. Let me give everyone a minute to get caught up. Are you guys good in the room? Everyone connected up? Okay, and if you log in and find that this directory, the Hadoop Training folder, isn't there, please let us know in the chat so that we can try to help you out. Okay, just one more minute to give everyone a chance to catch up, and then we're going to take a look at this file. And then we'll, when we come back from our lunch break, we'll go ahead and compile and run this example program. Okay, so let's go ahead and start talking about this. You can follow along if you like, if you want to open a text editor with the word class.java, or just watch on the screen. We'll just talk about what's in this. This is pretty much the simplest Hadoop program that you can make. It's adapted from one of the canonical examples, just word count.java. We do some standard imports of all the libraries that we need to import in order to make this work. I'm not going to go into a great detail of those because I just want to talk about the Java specific bits, or rather the Hadoop specific bits. So the class is called word count. It implements a tool which includes some of the functions that the system needs to start the Hadoop jobs. And as I said, we have to have a map class and a reduce class, and this is the map class, which extends the map reduce base, implements mapper.
Question from the XSEDE account then?
Pardon?
From the XSEDE account?
Pardon? I don't understand.
Yeah.
They're asking if they can log in with their XSEDE password.
Yes.
If that's how they logged into Bridges, then that's how they would log into this node. And if they can't do that, that would be important to know, and we'll try to help them out over the lunch break. But if not, they can just follow along. They can actually access this file. For this part, they can actually see it just in the Bridges login node.
Can you repeat the directory?
Oh, sure. You can see it on the screen now. It's Hadoop-training-080916. It should be in your home directory, so your landing directory when you log in. Okay, keep going with this. So, first thing we do in our map function, because this is Java and we have to be extremely verbose, is we set 1 equal to 1. And what's actually happening here is we're using a fast counter variable type that Hadoop provides. So we set 1 equal to 1, and we set basically a placeholder for each word to go in. Number of records, input file. Here we pick up the job configuration, and this is important. We're going to see this when we submit our jobs later. This is how you pick up all of the options that you might want to apply to your job. For instance, the number of mappers or reducers, the amount of memory to use, things like that. Okay, we're also going to check to see whether we should be looking case sensitive for our word count. Whether there's any patterns we need to skip. By default, we do not. And print an exception if we throw an exception if we have a problem. Okay, here's the function that parses the skip file. We're not going to go into great detail about this, but okay, and here's the actual map function. Okay, so the map is going to take a key and value pair. Again, all of the information that you pass into a Hadoop function is going to be in terms of a key and value pair. Sometimes it's sometimes the key or the value might not be an important piece of information. You might actually be passing it one important piece of information, but you always pass them off in pairs. And in this case, the key is going to be the position of the file, and we don't do anything with it. And the value is the line of text. And we're going to apply the function, the map function, to each line of text. Okay, and this is going to output pairs of the word in question and a number, and that pair is going to be passed off to the reducer. Okay, so here's the reducer function. And it's very simple. While there's values left for each key, we simply add them all together. And at the end, we pass back an integer. We pass back the key and an integer to tell us how many of each one we found. Okay, finally, down here at the bottom, we have the run function, which picks up the job configuration. Sets job name. This is all generally just kind of boilerplate stuff that you would throw into almost any Hadoop program, but it's necessary in order for things to run. And you'll see that if you don't want to do all of this setup, you can again write in a language that's maybe a little less verbose or a little more forgiving about what's included and what's not. But we set the job name, the output key and value class, mapper, combiner, and reducer class. Input and output format. Let me just say a word about these real quickly. Text input format is the default input format for Hadoop, and if you pass text in, it's going to break it into 128 megabyte, again by default, depending on how you've arranged your HDFS blocks. And each map function or each map worker within the cluster is going to get one of those blocks to chew on, and often a single data node will have multiples of those running at a time. And it's going to set the key and value for each line. The key will be the position in the file, and the value will be the line itself, the actual text. There's other ways to do input and output. You can do it as just straight data. There's actually, in the documentation, there's a whole bunch of different kinds of input that you can do, and you can even make your own classes so that you can arrange your data the way that you like, but text input format is the default, and it's the easiest to demonstrate with examples. So. Okay, this is setting up the file for the input and output. Job client run job, this actually runs the job, and then returns 0 on success. And then here's our main function that uses the toolrunner.run function in order to run the job. Okay, so those are the components of a basic Hadoop program. Okay, I'm going to show you real quickly this process, and then we're going to actually take a break for lunch. And well, yeah, I think we have time to do this. Okay, I'm going to run through this process once myself, and then we're going to all do this together. But don't, no need to follow along right now. Let's see. Okay, so we have a special invocation for compiling Hadoop stuff and using the Hadoop libraries, which we use Hadoop's own sort of built-in compiler and libraries here. Not very exciting, but we get the class files. Okay, this is actually in the slides. And then we do the packaging. So Hadoop will expect your programs to be in the form of a jar file. Sorry, I found the wrong command here. Just copy it like everyone else. Okay, when you've done that, you'll have a wc.jar file, and that's actually the binary that you're going to be passing off to the Hadoop system in order to submit your first job. But we're going to hold off on doing that. I think this is a good time to break for lunch, right, Tom?
Sure.
Yeah. Okay. So we're going to go ahead and take a break and meet up again in 2 p.m. Right?
Yes.
We'll pick up again at 2 p.m. and we'll start the hands-on with the Hadoop, and then we'll talk about Spark as well. Okay. So see you in a little while.
2 p.m. Eastern time.
2 p.m. Eastern time, yes. So sorry for those of you who might not be on the East Coast.
Hello, this is Georgia State University.
Yes, hello.
We have 4 users who were unable to actually get on Bridges, and I was wondering if you guys could help us out because their passwords keep getting denied, and they have the XSEDE portal. They actually have the local user ID as well for Bridges. So
Okay.
What should they do?
So they're not able to get on Bridges at all, as opposed to
Yes.
Okay.
Send the
Is there a
username.
portal? I'm sorry, go ahead.
Send the usernames to Tom Maiden.
Okay, we'll do. All right, thank you.
All right. Anyone else having any problems right now that we can address over the break here? Okay. Well, if anyone has them, get in touch with us, and if not, we will pick up again in a little while. We'll give everyone a few more minutes to address any problems they've had before we resume. Get things straightened out. We're going to go ahead and move into the hands-on portion of the Hadoop section here. So recall that we are connected to R741, the name node of our little cluster. And we should be in the directory Hadoop-training-080916, where you will have some files. If you didn't already do the compilation, then you won't have these class files, but we will review that in just a second. Okay, so let's go back over this. So this is the command to do the compilation. If you haven't done this, go ahead and do it now, and let us know if you have any issues with it. I'm going to give everyone a couple minutes to get caught up with it. And just one little word of caution about the slides. If you have them open, don't just copy and paste out of them. It'll work for some commands, but some of the punctuation has been Microsoftified, so it won't translate right when you try to paste it in, although it will look okay.
It brought 2 notes for me.
Just warnings, I think. Yeah, I should mention also it's going to leave a couple of warnings. Let me do this one more time so everyone can see it. It's going to give some warnings because there's some things that are deprecated that will be probably removed from the future release that are included in this example. All right. Make sure you pay attention to the capitalization of word count. The C is also capitalized. Okay. So word count.java uses a deprecated API and recompile with --excellent deprecation for details. We're not going to go into the detail about that, but there's something in there that's deprecated for future releases of Java. So duly noted. Could not find mail class. Okay, I see a message about what directory should we be in. For me, it's this one, but it's going to be different for you. So it's actually, if you go from your home directory where you launched, where you logged in, you can just type cd enter to get there if you're not there. You're going to cd into Hadoop-training-080916. If for some reason that's not there, let us know. There were a couple of users that may have had issues. The solution is simple. If it's not there, you just copy it out of the /temp directory. But okay, whoever had the mail issue, I think you may have mistyped main. The command is this. Yes, if you have those things, you're in the right directory. Sorry, I'm responding to chats as they come in here. So. Everyone else finding this okay and doing the compilation with no errors?
Bash Hadoop command not found.
Okay, whoever has that issue, can you tell me what the host name you're on is? Are you on R741?
471.
It should be 741. Okay, yeah, that's gonna, whoever's running a Java. Yeah.
Host name Durant-ER006 case and do-.
Okay, yeah, you are still on a login node. You need to do SSH space R741. Looks like this. And then log into this node, and then all the commands will be there. The Hadoop is not installed on the nodes that don't run a Hadoop cluster typically. Okay, any other problems before we move on? Okay. Let's go ahead and jar this up. So we've got our class files now that we've compiled. Hadoop expects a jar file, so we run jar cf create files jar wc.jar, and then we're again pay attention to the capitalization. We're going to compile our class or pack our class files up into this jar, and we have wc.jar. If anyone has any problems doing that, let me know. Okay. Okay, don't do this just yet, but I'm going to go ahead and do the submission, and then everyone else follow me. So, command to submit this. I think I have this in the slides. Yes. It's on this slide, but we'll go ahead and just do it over here. Oop. What's wrong? I'm going to tell you what each part of this means in just a second. Okay, so Hadoop is the binary that actually runs this. We're telling it to expect a jar file, and the jar file is wc.jar, which we just created. The class we're going to run is word count. And this is going to be the input. Now, this is interesting. If you do an ls for this on your system, you're not going to see it. This is /dataset/complete.txt. This is the complete works of Shakespeare all concatenated into one large file. And it lives in the HDFS in the distributed file system. So if you do Hadoop space DFS space -ls/dataset/complete.txt, you'll get something, but you won't see it in the regular file system. But we store our data in there so that it can be easily accessed from the worker nodes. This argument here is going to tell us where we want to put the output. I'm creating an output directory called output-0809. You can just call it -output or just output or whatever you like, really, as long as it's unique. You will find, incidentally, that a lot of times when you run your first Hadoop programs, particularly with the examples, if the output directory already exists, it will give you some very hard to understand errors, and often just deleting the output directory and starting fresh will solve your problem for you. Okay. Then finally, we're going to pass a command line option for configuration for the job off, -d mapred.reduce.tasks equals 2. We're going to use 2 reduced tasks instead of the default, which would be 1 for this relatively small file. Just to demonstrate that this can be done, and you can look in the documentation, there's a link at the end of the slides that gives you a comprehensive list of all the options that you can change for the configuration. And if you're administratively inclined, you can change a lot of these things in the configuration files as well, but changing them for each job is possible like this. So I believe we're going to get a warning about that one, another deprecation warning, if I remember right. Nope. Something went wrong here.
I think you have a typo in the complete.
No, that's not it. No, the error is it's not finding the class word count, which it should. Sorry, we're having some technical issues today. Sorry, we might have the wrong version of this word count in here. Hold on one second. Okay, I apologize for all the technical snafus here. There was an older version of word count.java, and that's what ended up in the ended up getting populated into your home directory. So I'm going to have to ask you all to do me a favor and run the following command. Well, commands actually, in order to make this work. So the first one is to remove the incorrect jar and class files. So rm count.jar, rm star.class. And then cp/temp/wordcount.java dot. My apologies.
Excuse me, could you please show the commands again?
Yeah, I'll show you the compilation commands in a second. You'll need to do these things first in order to make it work. We've done this training a whole bunch of times in the last few years, and I think that one of the scripts that populated the home directories with the source file populated it with an older one. So.
Your WebEx screen is not.
Oh yes, I'm sorry. My mistake. Here. Okay. Here's the commands. Okay, we need to remove the old jar and class files so we can make the right ones. Okay. Anyone have any? Hopefully, no one's have any problems with those. All right. So again, we do the this command to compile. I think we won't get a deprecation warning on this one. Yeah, so in the last few years, Hadoop has gone under a lot of development. It's gone from the 1.x to 2.x series of releases, and we're all the way up to 2.7.2 now. The structure of a lot of things has changed, and the example files that, or example programs that used to work, a lot of them have been broken with relatively recent upgrades. Even ones that worked with some of the earlier 2.x releases aren't compatible anymore. Okay, so I've already done this. Let me just show you real quickly. Well, no, let's go ahead and do this. Let's go ahead and submit our job. Once you've got this jar created and you got it with no errors, and of course speak up if you have any issues, this is the command to submit your first Hadoop job. I'm going to leave that up there for a minute so everyone can see it. And then I'll show you what the output looks like. Okay. So I had my output set as output-0809, so I'm going to do Hadoop dfs-ls. You can also, again, do hdfs if you want instead of Hadoop as the command there. Both of them will work. The home directories in Hadoop land are typically /user with an E, which is going to be unfamiliar to those of you who are accustomed to Unix. And then your username. Okay, I've got a bunch of files here. We're going to look at output. Show you 9. Okay, so we've got 2 files here. I'm going to make these a little smaller so we can see them all in one line. Let me know if anyone has trouble reading any of this. So there's 2 files here. One of them is an empty file, 0 length, as we can see. That's just called _success, which just indicates that the job succeeded. And this one is actually going to include the output of the job. And it's a fairly big file. We'll look at the beginning of it. The permissions and ownership work very much like in Unix. So we've got here read and write by owner, read by group, and read by everyone. Begil is the owner, the supergroup is the group. And then here is the modification time, path, etc. Okay, if you're doing this, make sure that you pipe this to something, because otherwise it's going to be a very long cat on your screen, or you're going to have to Control-C out of it. But I'm going to pipe this to head just so you can see the first few lines of output. Okay, so this was a pretty naive word count that didn't do any kind of checking to see whether there was punctuation. So the first thing that appears is an ampersand-C, et cetera, et cetera. Let's look at the first 100 lines. And here we get into still with punctuation at the beginning, but getting down to the C's and so forth. And it tells us how many appearances of each of these. There's 2 commends with an apostrophe at the beginning, 2 comes with and without commas, etc., etc. Okay. It's just a word count. There's nothing special about that. But if you made that work successfully, then congratulations, you have submitted a Hadoop job. If you're having any errors or problems doing this submission, please let me know. And if everyone is good with that, we can move on to the next section, I think. Okay.
Hello?
Yes.
Excuse me, yeah, we have a question. We submitted the job, but it seems to be frozen. It's not.
Takes a while. Takes a few minutes.
2 minutes? Oh, okay.
It took me 5 minutes.
Okay, probably it's processing. Right.
Okay, well, there's 400 people on a fairly small cluster, so you may be queuing briefly, but it should finish without too much trouble. Did all of your jobs eventually finish? Not yet, still. Pardon? You're still waiting for it to go through. Okay. Let me see here. Okay, it looks like we've got 76 people submitted successfully. Accepted. Running. Okay, well, there are a lot of us submitting, and we've actually asked for more resources than are necessary to do this tiny job. So it may be the case that it'll take a little while for it to submit.
If you take a breather here, this might be a chance to tell people, remind people that they're going to have their accounts for the whole week. So they don't have to panic right now if you can't do every single exercise immediately. Not only is there exercise session time coming up, but they have
John makes an excellent point in case you couldn't hear, which is that you're going to continue to have access to your accounts for the next week or so in order to run any of these examples again that you might have, might find it slow to run right now when everyone's trying to run at the same time, and you also are going to get some more chances to run whatever you like later this afternoon. But you'll find, let's see how many of these we have submitted, accepted. We have 96 pending still, and 4 running at a time right now. and 85 completed. So there's quite a few people. This is not a typical workload for a Hadoop cluster. Typically, you'll run one job that runs for a long time and not be submitting a whole bunch of them all at once. It can handle them, but it's doing quite a bit of spin up to do each one of them. In fact, I mean, the job itself is by far the shortest part of what's happening here. But it's communicating with all the nodes and organizing the jobs, etc. Okay, well, I'm not too worried about it if your job hasn't completed, but if it hasn't by the time we get through the next section, then we can just cancel it and move on and then try to run it again later. Okay, let's talk about the ways that you can configure your job submission. We showed you that you can set the number of producers. You can also set the number of mappers. You can set general Java options. And, pardon? Yeah. So for instance, if you want to deal with your garbage collection or set memory for Java, you can do that. And there's other various parameters. And again, there's going to be a link at the end of the slides that will take you to the documentation for those things. Okay, let's talk very briefly about monitoring. You may have seen that I've opened this up, and if you have the proxy working, then you can follow along with this. So there are three main web interfaces for Hadoop that we're going to be concerned with. The first one is the Yarn Resource Manager, which allows you to track your jobs. That's the one I was just looking at. This is the address for it. The second one is the HDFS, which has a few interesting properties of telling you, it's mostly an administrative interface to let you know about the status of the data nodes, but also an interface that lets you use the web to browse the file system, so that can be useful. They've changed it recently. You used to be able to actually view the files directly, and now you can download them, which for most purposes is good enough. And then this one is the job history server, so if you want to find information about what's been running on your system or what happened with a particular job, you can use that. Administrators will have to note that that has to be started separately. It's not part of the default package that gets started when you start everything. Okay, so this is the 8088, and we're actually in the accepted jobs tab here. So let's refresh and have a look here. Okay, so there's only 85 pending now, 107 have completed, so we're slowly working through the backlog. Okay. Questions about the web interfaces? Okay. Oh, actually, let me just show you real quickly the HDFS interface. So this is the screen you see when you first look at the HDFS interface. It shows you the capacity. We have 34 terabytes of storage in this little cluster. 10 terabytes used currently. And we have 10 nodes that are up, 10 data nodes. Okay, over here, there's a bunch of information here, information specifically about each data node, vault failures if there are any, snapshots, which we have not done for this training cluster. Information about startup for when you're first starting up the system, which isn't useful to us right now. We can look at the logs, or we can look at the file system, and this is what we're particularly interested in. This is showing us the root directory. Again, user with an E, and here are all of the many usernames here. Here's mine, so that's what we'll look at right now. Up at 0809, and this is what we just looked at. So if I click in here, it's going to give us access to this file. We can get information about the blocks. It's only a one block file because it's small. And then we can download the file and deal with it locally if we want to. And we can just see information about it here and about where it's replicated to. Okay. All right, so finally, troubleshooting. Inevitably, when you start trying to run and work on Hadoop jobs, you're going to have quite a few errors. And so the very first thing to consider is to carefully read the stack trace. If you're familiar with Java, then this is going to be nothing unusual to you, but if you don't use it very regularly, you're going to see a giant wall of text, but usually only the first 2 lines or so are really the answer to what the problem is. And oftentimes, though, that problem is going to be pretty obscure, particularly with Hadoop. So, of course, Googling the issue could be your friend. But also, don't forget to look in the logs. A lot of times, you'll find information in the logs that you're not going to be able to easily find in that stack trace that you get from your job right at the command line, in particular for system issues. And again, this might be more for administrators, but certainly there are logs from your job, and you can configure what you're logging. So you can get a lot more information about where and when things are going wrong. Checking system levels is also important, especially if you're running, for instance, like a lot of people will set up a test cluster in a VM or a small collection of VMs without a lot of space, and then you very quickly run into problems with disk or memory, or especially if running VMs on the same machine, you find that there's a lot of contention for resources all at the same time when you try to run things. Those can explain the problems you have. And finally, you can always try changing the job options and see if it works, reduce the amount of memory that you're requesting, et cetera, and you might get your jobs to run faster or to not crash on you and so forth. So those are just a quick overview of the kind of things to look at whenever you're having problems. Okay, let's talk about Hadoop streaming. So Hadoop streaming is an alternate method for programming MapReduce jobs that does not rely on Java. You can write your MapReduce jobs in any language you like. You can do it in C. You can do it with Bash scripts. You can do it with Python, which is what I like to do. And it's a very useful method for doing it. The way we do this is instead of using the built-in system to use the Java map and reduce classes to handle the handoff of information between the mapper and reducer. Instead, we're going to use a script for each one. The map and the reducer are each going to take a series of keys and values on standard in, and then pass more keys and values between each other, and then output the output from the reducer. The text class is the default for input and output, which can either be the whole line or everything after the first tab, and it's configurable. And this is an excellent way, even if you're going to be writing your program ultimately in Java, to do some fast prototyping, to make something in a convenient scripting language, and then to optimize it later to make it work as fast as possible. You do lose a few options that are available to you with Java, and you probably lose some performance, but still, there can be advantages to it. Okay, so let's talk about a simple example. This one is just using the bash commands word count and cat. So we're going to do something similar to what we did where we do a word count, but we're not, instead of using a custom-written Java program, we're just going to use the simple utilities that are available to everyone. So let's go ahead and type this in here. You guys can follow along if you like. It's probably going to, I'm guessing, take a little while, given that we have a little bit of a backlog there. But
what should be the output of once it ran?
The output will be, if you look in your output directory that you specified, you're going to find two files, a success file and then a part-00000 file, and that will contain the word count of each word. So we leave off the jar argument since we're not, the jar that we're handing it is a built-in jar rather. Okay, and I'll tell you what everything here means in just a second. Let's finish transcribing it. Okay, so Hadoop, we're running the Hadoop job. The jar argument, the jar we're handing it is the streaming jar that tells it expect input to go to and from scripts. The input for our program is going to be a directory full of the individual Hadoop or individual Shakespeare plays called /datasets/plays. -output, and we're going to put it in streaming out 0809. -mapper. The mapper in this case is going to be /bin/cat, which is just in the regular file system, and the reducer is going to be /user/bin/word count with the -l argument, so we can count up the lines. Okay. So that's going to run the job, and then when that's done, we'll take a look at the output. It's going to be very similar, but What's interesting about this is that we're using very simple tools, and if you remember what I told you earlier on, that really what Hadoop is doing under the scenes is very similar to just piping stuff between scripts. In this case, we're literally piping it between scripts. But it's interesting to note that the only reason we can get away with identifying these scripts is because they exist already on each of the nodes. In other words, each one of the worker nodes has exactly these programs in exactly these places in their local file systems. We're going to see in the next example that there's a way of dealing with it when you do not have them in place. So for instance, if you want to write a custom map word reducer, you're going to have to pass them off to the system. Well, let's see how long. One other thing that is interesting. Let's see if it gives us here. Yes. So if you look at the output of your job here at the beginning of it, it gives you a direct URL to track your specific job. It's going to be different for everyone, so you don't want to copy what I wrote unless you want to look at my job specifically. But okay, it just says that it's in the accepted state, so it's waiting until we have the chance to actually run it. We're still pending a bunch of applications. Okay. So let's look at another example, and we'll run this one in a minute too. The command line for this one is very similar. Hadoop jar, and then we identify the streaming jar. And this star is here just to indicate that it could be any version, whichever version you're running, but the file will be in the same place. So this one happens to be 2.7.2. And here we're passing off file mapper.py. So we're telling the system, I have a file that we need to distribute to all of the worker nodes, and it's called mapper.py. So hand that one off, and then the mapper will be that script. Same deal with the reducer.py. We'll look at what's in those in just a second. The input is the same as with the shell script example, and the output we can call pyout or whatever you like. I'm going to have to change the name because I think the directory already exists in my home directory. Okay, let's just put that on hold for a minute. Okay, so the mapper is very short. We're going to take each line from standard in, strip any white space, and split it. And for each word that we find, we're going to print that word in the number 1 with a tab. Okay, so the key that we're handing off to the reducer is the word, and the value in every case is just going to be the number 1. And it's going to add all those ones together to get a full count. The reducer is slightly more complicated, but not very much, just because it has to handle all the different keys. We add the count for each one. And once we've done all the keys, we print them each out. Each key will be a word, and each value will be the aggregate number of numbers the aggregate number of ones that were detected for each word. Okay. So I'm not going to go into a lot of detail about that, but again, the point is that you take the input on standard in and process each key and value pair, which will each be aligned, separated by a tab by default, and configurable if you want to change the way that works for the needs of your data. Okay, so it looks like this finished. Incidentally, if you haven't already seen this, here's an ls at the datasets directory. It includes that complete.txt file we were talking about, the plays directory that holds a bunch of plays, each play in one file, and then this is something we're going to get to with Spark later. If you want to, just like in Unix, you can omit your home directory and just start typing the name of a directory that's in it. So this this is equivalent to /user/bgill/streaming-out-0809. And there's that file, and if we do wish that Max had a home key. So the first 10 lines of that. Oh, I'm sorry, this one actually is just going to give us a, this one actually just counts the total number. This was just the word count, the total number of lines in the Shakespeare file. I was expecting the Python one. This is much simpler. This was the bash example still, so I'll just show you how to submit the Python streaming job. It's the same basic principle. Oh. Okay, so it's submitted the job. Okay, and you're going to find that the output looks pretty similar to what we got with the other program.
One question. So here you're saying file mapper and then again mapper?
Yes.
What's the difference?
Okay, so the -file command is the command that tells the cluster distribute this file to each of the nodes, because that file actually only exists on the name node. And if the data nodes tried to run it, the worker nodes, they would get a file not found error. So you have to tell it, take this file and distribute it. We didn't need to do that, if you recall, with the shell script example, because all of the worker nodes also have the same, they also have the built-in binders.
And after that, when the second one, mapper, say that each of this running the mapper file.
Well, that's true, but I mean, the point of having the two commands, the -file says distribute the file,
Okay.
-mapper says each node use the file.
Use it.
Yes. And -reducer, same thing, to use the other one as the reducer script. And they don't have to be called mapper or reducer, they can be called, you know, grep for whatever, or you can call them whatever they actually do, or whatever you want, really. I mean, you can call it.
The name of the file.
Yeah, the name of the file can be anything.
There's a comment in the chat.
Yes. Up to Hadoop. Okay, if you're trying to run that directly, the Hadoop streaming jar, rather than use it as an argument to Hadoop, then that might be your problem. If you forgot this part at the beginning, you would probably get that error. This is to the Youngstown folks. Let me know if that wasn't the issue.
You remind if someone needs to mute.
Yes, could you check and make sure that you're muted? Someone is, someone's still making some noise.
I'm getting an error with this command.
What's the error you're getting?
The not a valid job.
Okay. That probably just means you have a typo somewhere. You didn't copy from the slide, did you?
I did.
You did, okay. Well, what that does is replaces the dash with a different character. So if you, Microsoft, whenever it reads a dash, inserts its own different character. So if you just change all the punctuation to be real dashes, it should work. Okay, well, we've run almost 300 Hadoop jobs already this afternoon, which isn't so bad, especially for such a small cluster. Yeah, I see it. Okay, just a reminder to everybody if you copy from the directly from the slide, it's probably going to create some problems for you because the punctuation in the Microsoft applications will be slightly different characters. Okay, if there's no more questions about submitting this, we'll give it just one more minute, and then we're going to move on to Spark. I'm not going to hold off and wait on the output of this because it's really not going to be anything exceptional. It's going to look a lot like the other word count output. But this is how you run a Hadoop streaming job, and again, lets you write it any way you like using whatever you're most comfortable with in terms of programming language and frameworks. So, thank you.